yeah, we started talking about solutions on Wednesday. And so you had sort of the introduction stuff. So we talked about what the water molecule and what being polar or non-polar means and how that impacts, like if things will dissolve in water or not dissolve in water. And we talked about how different things dissolve. Like ionic compounds, if they dissolve like salt, which is an ionic compound, it will split apart into the positive and negative ions. And so ionic compounds are also, when they're dissolved in solution, they're called electrolytes because they will conduct electricity because of the positive and negative charges floating around in the solution. Covalent compounds that dissolve in water are usually polar covalent because non-polar substances don't dissolve in water, they can't mix. And so when you have polar covalent things that dissolve in water, they don't split apart in ions. They stay like one molecule clumped together. And because of that, they are called non-electrolytes because they don't conduct electricity in water. Okay. We also talked about the difference between all right. And then we also talked about the difference between weak and strong electrolytes. And that just means if something's weak, that means that the ions don't all split apart, like maybe only part of it splits apart. So it can still conduct electricity, just not very well. And if it's a strong electrolyte, that's going to be like your ionic compounds where they 100% completely split apart. And so they're going to conduct electricity very, very well. And they'll be like a bright light bulb and all that kind of stuff. Okay. So today we're going to talk about what's called solubility rules, because even though last time we kind of said, yeah, ionic stuff dissolve in water. Well, there are some ionic compounds that don't dissolve very well, like they only partially dissolve or they like just barely dissolve. And it's really not enough to say that it actually dissolves. And so we're going to talk today about the rules that we use to determine if an ionic compound will or will not dissolve in water. And so we're going to see the terms soluble and insoluble pop up. So if something is soluble, that means it can dissolve in water, okay, or in whatever your solvent you're using. If something is insoluble, by putting that prefix in front of it, that means it's not soluble. So that means it will not dissolve in water, okay, or it won't dissolve very well. And so we say that it's insoluble. And then you're going to have a kind of a list or a little chart of what we call solubility rules, where you're going to look for different ions based on the compound formula. And you're going to be able to determine if that ionic compound will or will not dissolve in water based on those rules. So I'm going to go through the information together. So this is your only assignment for today, is to make sure you've gone through this. And then there are some questions throughout, and then there's some at the end. Now at the beginning here, you can see this little animated GIF here, and you can see it looks like it's like magically making yellow. Well, what's really happening is what's in the test tube is one solution with an ionic compound dissolved in it, and they are adding drops of another ionic compound dissolved in a solution. And what happens is when those two ionic compounds in solution come together and they react, one of the products that's formed from the chemical reaction is insoluble. Because when the ions come in contact with each other, they're not soluble. And so that yellow that you actually see, those are actually tiny little flecks of solid substance, because it won't dissolve. And so we call that a precipitate, which is a word we're going to see on the first page or two in just a second. And so anytime you see something like this, and it's not always yellow, this one with yellow, this is usually lead. It's usually lead iodide, I believe is what it is this yellow color. Some of them are white. Some of them are kind of a creamy color. There's some that are blue, some that are kind of dark red, green. The color just depends on usually what the elements are, what the positive metal ion is, and what you're pairing it up with, okay? But anytime you see something like this, whether it's white, yellow, red, whatever, this is forming an insoluble product. And so if you let it sit long enough, all of that yellow, it's going to settle to the bottom. And so it's going to look like it's all a clear solution on top, and all the yellow will be settled at the bottom of the test tube, and it'll look like little solid flecks. You'll be able to see like tiny little particles floating, okay? But it takes a while for it to kind of settle out with gravity. So as just a recap, we've talked last time about like what is a solution, and then these solute and solvent. So this is a recap, because there are some solutes that will not dissolve in the solvent. And that's kind of what today's focused on, is how do we tell if a solute will dissolve in a solvent, okay? Because there are rules for the ionic compounds, all right? Normally, they usually dissolve, but as I told you guys, Soluble substances, they will dissolve in water or another solvent. The reason I say water is because probably like 99% of our solutions are aqueous, meaning you're using water as the solvent. There are very few that you don't use water just because water is that universal solvent, so it dissolves so many things, okay? Insoluble, they will not dissolve, okay? So I said sometimes they're called precipitates. So if you see the word precipitate, insoluble, those are kind of like synonyms, okay? So insoluble and precipitate both mean it will not dissolve in water. So that means it's going to stay a solid and you're just going to see little particles sink to the bottom. Soluble, they will dissolve in water. So a lot of times we'll say they're aqueous because aqueous means that it's going to dissolve and make an aqueous solution in water. Okay. So just a couple examples. We talked about sugar and salt last time. Sugar is soluble. Salt, table salt, which is sodium chloride, is soluble. They dissolve in water. Something like oil is not going to be soluble. It's insoluble because it won't dissolve. It's non-polar. Okay. I kind of already mentioned this at the beginning, but there's just like everything, the rules aren't 100% true. So not all ionic compounds dissolve in water the same way. Some of them partially dissolve. Some of them dissolve like so little that we call them insoluble because they don't dissolve enough for us to say that it's a solution. Okay. So this table on the left column, you have anions, negative ions. So some of them are just nonmetals like chloride, bromide, and iodide here, or sulfide down here. The rest of them are all polyatomic ions. So you have nitrate. These are both acetate. It's just two different ways that the formula is written. So you can either group all the carbons and oxygens together here, or you can write it out. This is what it looks like more structurally. So in organic chemistry, we usually see it written like this because it's more structurally correct. Sulfate, SO4 is sulfate. Carbonate and phosphate, we group them together because their rule is the same. Hydroxide, and then chromate and dichromate are together because their rule is the same. So the way that you read this, okay, is you look at the compound formula that they give you and you look, what's the anion? What is the negative ion? And you come and find it on this list. And then you go over here to the right. And so for example, if I have something with nitrate, NO3 in the chemical formula, and I look, it says all nitrates are soluble. So that means it doesn't matter what the positive ion is, any formula that has nitrate, it's always going to dissolve in water. Same thing for acetate. So nitrate and acetate, you don't even care what the positive ion is. If it has nitrate or acetate, it's always 100% dissolving. There's no exceptions. Now the rest of them on here, there are exceptions. And what an exception means is that it's going to tell you normally it will do this, except when it's bonded with certain positive ions. Okay. So chloride, bromide, and iodide, it says all of them are soluble. So normally if you have chloride, bromide, or iodide in a chemical formula for a compound, normally they're going to dissolve in water. The only exceptions are if you have chloride, bromide, and iodide paired up with one of these three elements, okay? So if it's paired up with silver, so if you have silver chloride or silver bromide or silver iodide, they will not dissolve. They will be insoluble because that's an exception. If you have lead chloride, lead bromide, or lead iodide, they will not dissolve because that's an exception. And if you have this mercury chloride, mercury bromide, or mercury iodide, they will not dissolve. Anything else that has chloride, bromide, and iodide is going to be soluble, okay? So the rest of the rules are written similarly. So sulfates, all sulfates are soluble. So normally sulfate will dissolve, except if it's bonded with one of these four: barium, lead, calcium, and strontium. So if you have barium sulfate, lead sulfate, calcium sulfate, or strontium sulfate, those are insoluble because those are exceptions. Anything else with sulfate is soluble. Okay. Now, the last four on here, if you notice, the wording's slightly different. So this one is for carbonate and phosphate. It says all carbonates and phosphates are insoluble. So now the bottom four, their normal thing is they do not dissolve. They are insoluble, except if they're paired up with certain positive ions. So normally carbonate and phosphate are going to be insoluble, hydroxide is going to be insoluble, sulfide is going to be insoluble, and then chromate and dichromate, all of these down here are normally insoluble. But for carbonate and phosphate, if you pair them up with ammonium or lithium, sodium, or potassium, those four are exceptions. So if you pair carbonate and phosphate up with one of these four, that makes it soluble. The exception is backwards for the bottom four, okay? And then same thing down here, all hydroxides are insoluble, except when you pair them with ammonium, lithium, sodium, potassium. So the same ones as carbonate and phosphate, but there's three more now, calcium, strontium, and barium. And then sulfide is actually exactly the same as hydroxide. I'm not sure why we didn't put this on one line. I didn't type this up. I would have combined these two together because their rules are exactly the same. They're insoluble except when paired up with ammonium, lithium, sodium, potassium, calcium, strontium, and barium. So their two rules are exactly the same for hydroxide and sulfide. And then the last one is chromate and dichromate. Again, they're all insoluble. And there's an E left off here too. It's a typo, and I couldn't correct it because it was an image that somebody made. Except when with ammonium, lithium, sodium, and potassium. So really, if you want to even like simplify this more, if you're writing it in your notes, chromate and dichromate and carbonate and phosphate, their rules are exactly the same. They have the same exceptions. So ammonium, lithium, sodium, potassium. So if you want to list all four of those together, so you don't have to write it twice. And then you could also write hydroxide and sulfide together because their rules are the same. Okay. And then if you also want to combine nitrate and acetate because they're soluble no matter what. So if you want to condense it down for whatever you add into your notes for you to reference for when we get to our test, you can actually combine some of the lines as long as their rule is written the same way. Okay. So how do we apply this? Okay. Step one, we're going to look at our formula and determine the ions. Okay. So for example, this one is AgCl. So the cation, the positive ion, that's the metal. So that would be sodium, or I'm sorry, not sodium, silver in this one. And then the anion is the negative ion. So that's always written second. It's usually the non-metal. So that's chloride in this one. The other example we have is CuOH2, and Cu is copper. That's a metal. So that's our cation. It's written first. And then OH is hydroxide. That's one of the polyatomic ions. Okay, so that's the anion. So that's the first thing, is identifying your cations and anions, because that's how you're going to read that chart and figure out if it's soluble or insoluble. So then step two, it says you look at the anion. So for the first one, we need to look at chloride. For the second one, we need to look at hydroxide. So if we come back up here to the chart, chloride is right here. It's on the third row. And the rule says all chlorides, bromides, and iodides are soluble. So normally it says on the chart, chloride normally is soluble. We look at the hydroxide, OH, here it is right here. All hydroxides normally are insoluble. So that's the basic rule. So we're saying normally chloride soluble and normally hydroxide is insoluble. And then the last thing you want to do is check for exceptions, okay? Because if they have exceptions, that might change it. So if an anion is normally soluble, but it's bonded to an exception, it'll be insoluble. And then the reverse is true. If normally it's insoluble, but it's bonded to an exception, that makes it soluble. So for AgCl, we said on step two, chloride's normally soluble, but if we look, it's bonded with silver, Ag. And if I go back up here, silver, Ag, right here, it's one of the exceptions. So for that first example, AgCl will be insoluble, okay? Because that silver is one of the exceptions for chloride. Now on the second one, we said that hydroxide is normally insoluble. And then if we look at the list of exceptions here for hydroxide, there are several of them, but copper is not one of them. So it is not bonded with an exception. So that means it's going to follow its normal rule and it will stay insoluble. Okay. So here at the bottom, you have a couple to practice with. So it's going to give you a couple of NaOH and then BeCl2. So it's going to give you a couple to practice with on the rules that you can check yourself just to make sure you're understanding how to do it correctly. And then here at the end, kind of your overall check for understanding on using these rules, it has the same chart that we just went over, and you have several compounds listed down here below, and you're just going to drag them to wherever you think that they go, okay? And then you can check yourself. So again, look at the negative ion, the anion first, find it on the chart and look at the rule, and then check to see if the cation is an exception or not, okay? And that will tell you which direction to categorize them as, all right? And so when you get done with this, make sure that you go to the last page and that you submit report and make sure that everything is completed before you submit it for your grade for today. Anybody have any